Hello everyone, I'm Zhongwei Zhang from the University of Science and Technology of China and HiDream AI. I'm glad to introduce our work named TRIP, Temporal Residual Learning with Image-Not-Prior for Image-to-Video Diffusion Models. Recently, image-to-video generation is a very popular task. According to different input conditions, we can divide the image-to-video task into several types: unconditional image-to-video, motion-driven image-to-video, and text-driven image-to-video. Our paper mainly focuses on the text-driven image-to-video model. Now, there are several challenges for text-driven image-to-video models, which requires the generated video to not only align with the text prompt and the image, but also maintain temporal consistency. This is the result of a typical image-to-video model. It can be seen that the generated video matches the given first frame and text prompt, but the video has an inconsistency problem. Typical image-to-video diffusion models often predict noise vectors independently for each frame, ignoring the inherent relation between video frames. Those methods fail to effectively model the consistency between video frames, making it easy for the generated video to exhibit sudden changes. To address this problem, we propose temporal residual learning with image-not-prior. Specifically, the image-not-prior is first attained through one-step backward diffusion process based on both static image and noise video latent codes. With image-not-prior as a reference, a residual path that employs send-UNet to capture motion dynamics and predict residual noise. And then, both reference and the residual noise of each frame are dynamically merged via an attention mechanism for final video generation. From the result, we can see that our trip have better temporal consistency. This is our network architecture. Trip performs the residual-like noise prediction along two pathways, namely the shortcut path and the residual path. The shortcut path computes the image-not-prior as a reference noise, and the residual path uses send-UNet to predict the residual noise with reference to the image-not-prior. By dynamically merging the reference and residual noise via a TNF module, the final noise vector for video denoising is attained. Here is the calculation process for the image noise pair. The first line follows the classical video diffusion process. By transforming this formula, we obtain the equation in the second line, where the noised video latent code can be denoised to the clean video by subtracting the added noise. The superscript I represents ith frame of the video. If we replace Z0i with Z01, we construct an epsilon, which represents the image not pair. As seen from the third line formula, it means that the noised video latent code can be denoised to the clean first frame latent code by subtracting the image not pair. Hence, due to the interframe correlation, it's sufficient for the send-UNet to predict the residual noise to capture motion dynamics. Then, using the TNF module, the image not pair and the residual noise are dynamically merged. Specifically, the network design of the TNF module is as follows. It's a transformer structure that includes self-attention and cross-attention mechanisms. Here is the final loss fraction. The epsilon mentioned here is our new noise format. To demonstrate the effectiveness of our method, we conducted experiments on the WebID 10 million dataset. Overall, our trip consistently leads to performance boosts against the existing diffusion-based baselines across different metrics, including frame consistency and FVD. Frame consistency is particularly important for us as it indicates the temporal consistency of the generated video. Figure 4 shows the performance comparison of the frame consistency by using different number of frames. The temporal consistency of trip across various frames surpass other baselines. Additionally, our model also outperforms existing models on the DTDB and MSRVTT datasets. Here is the visual comparison result of our trip with other methods in our paper. From the result, we can see that our trip has better temporal consistency. Finally, we evaluated the effectiveness of the trip module. As seen in Table 6, trip achieved better performance in terms of frame consistency and FVD compared to the trip minus model. From the figure 8, we can see that trip can generate more consistent videos. Here are the comparison results of our model trip with other image-to-video methods. From the video, it can be seen that our model generates video with better temporal consistency and more natural motion. Here are more video results generated by our trip. Thank you for your listening.